Next one we want to talk about is hydrogen bonding. Now, hydrogen bonding is a particularly strong form of dipole-dipole forces. It is a dipole-dipole force, but it's a really, really strong one. And so here's the way this works. Hydrogen bonding occurs when hydrogen atoms covalently bond with the three small most electronegative atoms, which are fluorine, oxygen, or nitrogen. So it's always a hydrogen bonded to a nitrogen, a hydrogen bonded to an oxygen, or a hydrogen bonded to a fluorine. There are no other situations we consider to be hydrogen bonds, even though there are some elements that have a higher electronegativity than, say, nitrogen, like, for example, chlorine. Nitrogen's 3.04, chlorine is 3.16. Because of the fact that chlorine had electrons in 3 energy levels, they're farther out, and so it has to be a small atom. And so for the most part, we don't need to figure this out. We just need to know if either one of these 3 things shows up, you're going to have hydrogen bonding, chances are. Because here's what happens. Hydrogen only has 1 electron, okay? And so if I have a hydrogen atom out here, if I drew out the Lewis structure for that, I'd have my 1 electron here in the hydrogen. And so it's going to then go to the fluorine, and let's say I put a fluorine in here. Fluorine has 1, 2, 3, 4, 5, 6, 7. But since it's going to covalently bond, then the hydrogen is going to share this pair right here. But since fluorine is really, really electronegative, it's going to take those 2 and it's going to pull them all the way over to the fluorine. And so that shared pair is really going to sit over here next to the fluorine. Now, what does that leave for hydrogen? Well, hydrogen doesn't have any other electrons. That electron that fluorine pulled over to get next to it, hydrogen now has no other electrons. All that's left with hydrogen is just the proton. And so we have basically sort of a bare proton. And so that's the term we sort of use here, because if we drew this out in terms of our HF and looked at sort of where the electrons would be in terms of like their sort of electron cloud, this electron cloud is going to be mostly a little bit over here, but really a lot over here. And so you're going to find those electrons mostly in this range, leaving this side only positive and this side mostly negative. This is a really, really strong dipole, much stronger than anything else that we're going to see in a bond. And the reason why is because every other element that we could bond to fluorine or oxygen or nitrogen or chlorine is going to at least have some electrons still around it because it has electrons in its lower energy levels. That's not the valence shell. Hydrogen has no other electrons. The one that it gave to bond to the fluorine or the nitrogen or the oxygen is the only electron it has. So when it gets pulled away from it, that leaves a completely positive side. And so over here, we have some pictures of some water molecules. And so we have our hydrogens right here, and then we have our oxygens that are right here. And so the red is the oxygen, the whites are the hydrogens. And down below it, you can see the same 3 molecules, but this time showing where the partial charge is. Blue indicates more of a negative charge, red indicates more of a positive charge. And, sorry, we flip that around. Blue indicates a more positive charge, red indicates a more negative charge. Because what you can see is that this oxygen that's right here, being more electronegative, has pulled the electrons in from the hydrogen, so that shared pair is going to sit sort of over here. It's pulled it in from here, that shared pair's here, and so it leaves these bare protons over here. And so these ends are going to be very, very positive. This end is going to be very, very negative. And so what's going to happen? Well, this little positive end is going to attract that negative end of a different water molecule, and it's going to pull them together. And so this little picture down here shows the same thing, is that you can see how that right here, that this poor positive hydrogen over here that's got its electrons pulled towards the oxygen is going to stick now to the negative electrons that are sitting on the oxygen. It's going to attract those 2 together. It's going to bond them together. And that connection, this connection right here, I'll draw it with a different color, this connection right here that holds these 2 together, or holds these 2 together, it's strong for an intermolecular force. It's weak as far as covalent bonds go. So this hydrogen bond that connects these together is much, much weaker than this covalent bond that connects the oxygen and the hydrogen, but it's still strong as far as intermolecular forces go. And so so hydrogen bonding creates a very, very polar dipole, and that very, very polar dipole ends up creating a really, really strong potential bond. Typically, what's going to happen here is if we have an N, O, or F bonded hydrogen atom, if it gets near another strongly electronegative atom in a very polar bond, the delta plus, the positive charge in the hydrogen atom, attracts strongly to the delta minus of the more electronegative atom. And so, like for example, if we had something like some molecule in a chlorine that's sitting out here, and we had our water molecule, it's over here, We said that the oxygen is going to end up with the delta minus. The hydrogens are both going to be little delta pluses out here. And so that chlorine, on the other hand, chlorine is a very electronegative element. And so what's going to typically happen is if this hydrogen gets near this chlorine, it's going to attract to it and it's going to stick to it a little bit. And so that's that hydrogen bonding here. And so that connection is our hydrogen bond. So as we said, hydrogen bonds are much weaker than covalent or ionic bonds, but they're often 4 to 5 times stronger than any other dipole-dipole forces. But they only happen if you have a hydrogen with a nitrogen, a hydrogen with an oxygen, or a hydrogen with a fluorine. So let's look at this water molecule. We already sort of shown it a little bit, but let's just take a look and see why this would, whether this would be a hydrogen bond or not. So we have an oxygen, and then we'll draw out the structure is connected to 2 hydrogens. So the first question is, should we see hydrogen bonding here? The answer is 1, do we have hydrogen atoms? The answer 2 is yes, we do. We have 2 hydrogen atoms right here and right here. Second thing we have to look at, see if we have hydrogen bonding likely to happen, is that are those hydrogens attached to a highly electronegative small element, specifically nitrogen, oxygen, or fluorine? The answer is yes, it's attached to oxygen. So we should see hydrogen bonding between water molecules, because what will happen is the little delta pluses, little positive charges that are out here are going to attract to other water molecules, to the negatives that are down here. So we have a delta minus here, and that's going to create a little hydrogen bond that will connect this water up to that oxygen. Same thing had happened down here. We might have another water molecule that's going to be off like this. And so what will happen is a little delta minus here, a little delta plus on the hydrogen. We're going to attract up, and we'll have a hydrogen bond between those. And so water is going to stick together really, really well. Now, what about a water and ammonia solution? So let's see if these would stick together with each other. We know the water would stick to water. We've already figured that out. That would hydrogen bond with each other. But would water hydrogen bond to ammonia? So water is H2O. So once again, we're going to draw out this little structure right here, H2O. Ammonia is, if you remember, we said this earlier in this lesson, is NH3. And so that means I have 1 nitrogen and then 3 hydrogens that are out here, sticking out from it. So we already know there's going to be hydrogen, potentially hydrogen bonding in water because of the fact that it's got a hydrogen and it's connected to one of those 3, hydrogen, nitrogen, or fluorine. Now what about this ammonia? It has hydrogens, definitely has those out here. And then are they attracted to either N, F, or O? They are attracted to N. So we should see some hydrogen bonding going on here. And so what will typically happen is these little hydrogens, which remember are little delta pluses out here, they have a little positive, partial positive charge, are going to attract to this delta minus that's on the oxygen, and so they'll stick together like that. And so we would see hydrogen bonding between water and ammonia because we have both the hydrogen that's got its electron pulled away towards either nitrogen, fluorine, or oxygen. We have the oxygen, which is a very electronegative element, so it's going to have that negative charge. It's going to attract towards that bare proton of the hydrogen. All right, let's try next one, acetic acid and water. Down here I have the acetic acid. So let's look. Are there any potential hydrogen bonds that could form here? So what we're going to do is we're going to look at this. Let's look at our bonds going sort of from left to right. So we have an H to C bond. So is that going to be a hydrogen bond? Well, 1, do we have a hydrogen? The answer is yes, we do. So that's our first bit. Second thing, is the hydrogen bonded to either nitrogen, oxygen, or fluorine? It's bonded to carbon, so no. So we should not get a little positive charge out here very much. We're not going to have hydrogen bond. Same thing here, hydrogen to chlorine, or sorry, to carbon. So we will not see a hydrogen bond coming off this one. Carbon to hydrogen, not see a hydrogen bond here. Carbon to carbon, no hydrogen, so we can't do that. Carbon to oxygen, not going to be a hydrogen bond there because there's no hydrogen. Carbon to oxygen, not going to be a hydrogen bond there because there's no hydrogen. Here's a hydrogen. Is it bonded to either oxygen, nitrogen, or fluorine? Yes. And so here we very well might see a little, so we have a delta minus over here, delta plus there. So we very well might see hydrogen bonding off of this one, but only if it can get through next to another electronegative substance. And so there are 2 ways this could happen though, because the other part this is mixed in with is water. And so if we have water molecule in here, what we know is that water molecule is going to do what we saw before. There's an oxygen, I'll hook up the 2 hydrogens out here. So that oxygen is going to end up being very electronegative. It's going to have a negative charge because the hydrogens are going to have a positive charge. And so that's a delta right there. And so that means we should see a hydrogen bond between the oxygen and the water molecule and the hydrogen in this acetic acid. Second thing that would happen is, what if we had a separate acetic acid molecule out here? There is another way that we could see hydrogen bonding because there is one other very electronegative element that sticks out of this acetic acid, even if it's not hydrogen bonded, and that is this oxygen. this oxygen is going to pull electrons in really tightly. And so if we were to have this one with an acetic acid molecule that was sort of flipped upside down, I'm going to see if I can draw it out here. So we have our H right here. Actually, I'm going to briefly, just for right now, erase that just so we have space on this. So we have our H right here, and that's going to go over to an O, and then that O is going to go, see if I can, once again, I'm going to try to do this upside down. It's going to go over to a C. That C is going to be double bonded to an O right here. If you notice, I'm doing the exact same molecule, just upside down, then the carbon right here, and then the 3 H's that come off the edges. So hopefully you can see that that's basically that these two molecules are exactly the same thing, just flipped upside down. But I want you to look at what happens here. This hydrogen right here is going to have its little positive charge. This hydrogen is going to have its little partial positive charge. They're both hydrogen bonded. They're both very, very positives, and they're going to attract to any electronegative element that's nearby, and that's one right there. And that's one right there. And so we're going to get hydrogen bonds even between the acetic acid molecules because of the fact those can line up. If one molecule sort of flips around upside down, it'll sort of fit in and they'll hydrogen bond together. So we'd expect to see very, very strong intermolecular forces between acetic acid molecules with each other and between water and acetic acid. Let's look at a very interesting case of hydrogen bonding that shows up. DNA. You know, DNA has this nice little sort of double helix form right here, and so it's got those two like that, and then within the DNA it's got these different bases, right? Adenine, thymine, cytosine, guanine, and so and then for those we said that it sort of unzips and rezips. Well, what actually zips these together? Well, it's hydrogen bonds. So over here on the right side we can sort of see each of these, the molecular structures of each of those DNA bases, and one thing that you sort of notice here is there is some hydrogen bonding going on here, and so for right now, ignore these little guys right here because it's actually showing the hydrogen bonds. So let's just take a look at let's say adenine first. So adenine right over here has a hydrogen that's attached to a nitrogen. So that's going to have something potentially a hydrogen bond. There's a nitrogen attached to a hydrogen, potentially a hydrogen bond here. Hydrogen attached to a carbon up here isn't going to count because it's not attached to a nitrogen, a fluorine, or an oxygen. On the other side, we have a hydrogen attached to a nitrogen right there, and so that could possibly be a hydrogen bond here. But they'll only hydrogen bond if they're able to get next to another electronegative element. And guess what? Nitrogen is another electronegative element, so we'll see hydrogen bond there. Oxygen is an electronegative element, so we'll see hydrogen bond there. And that is why the adenine and the thymine will stick together, because those match up with each other perfectly. If you look at the size and the shape of these, those two hydrogen bonds, the two hydrogens that can hydrogen bond, are matched up perfectly with something that they could hydrogen bond to. Now, down the bottom, we have our other two bases, and you can see we have a potential for hydrogen bond here, and one here. Because that one goes to the nitrogen, this one goes to this nitrogen, this one goes to this, sorry, not that oxygen, I'm looking at the wrong side here, that's not part of the same molecule. This one goes to this nitrogen right here. And so we can see hydrogen bonding because this hydrogen could attach to an electronegative oxygen right there. This hydrogen could hydrogen bond to that electronegative nitrogen right here. This hydrogen could hydrogen bond to that oxygen right there because it's more electronegative. And so we have these nice little hydrogen bonds that will hold these bases together, that will zip up our DNA and keep it connected so it doesn't come apart, but they're not so strong the DNA cannot unzip itself whenever basically it needs to make a copy of itself. And so that whole process of transcription is able to occur because these hydrogen bonds are weak enough to be broken fairly easily without breaking up the whole molecules. It's not a covalent bond, but strong enough it's able to hold the DNA together. And it's because of the fact that they have the right shape so that each one of those hydrogens that are attached to an electronegative thing is near another electronegative substance, so that the negative, partial negative over here, the partial positive over here will attract to one another. Last type we're going to look at of intermolecular forces are called London dispersion forces. They are intermolecular forces that exist between all atoms and molecules. All these other cases have been sort of special cases. It has to be a dipole, has to be an ion, it has to have hydrogen attached to an H or to an F or an O or an N. But for London dispersion, it's every single molecule, even those that are non-polar. So it doesn't matter if it's polar or not, it will have London dispersion forces. And these exist due to instantaneous dipoles, which temporarily form as the electrons move around their orbitals. So let's take a look at this situation right here. Let's say I have two helium atoms. These are probably going to have the weakest intermolecular forces of anything you'll run into because they're very, very small atoms and they attract their electrons very, very tightly to each other. They don't even form covalent bonds or even ionic bonds, but they do form London dispersion forces that attract together slightly. Here's why. Normally, the electrons in the helium, it has 2 of them, are sort of evenly distributed around the helium atom. You know, they want to get away from each other, so they tend to distribute themselves nicely, spread evenly here around it, but that doesn't always happen. As these electrons sort of buzz around the atom, they move around, occasionally what will happen is they may end up both on the same side. Well, if they both end up on the same side of the atom, just by chance, we're going to end up with a situation where we have a negative charge on one side of the atom, a positive charge in the middle, which means that we have a very, very temporary situation where you have a partial negative charge on one side, a partial positive charge on the other. This won't last long, and we're talking instants. We're talking basically, you know, fractions of a second, because an instant later those 2 electrons are going to buzz back over to the other side. They'll be spread back out again. But temporarily, we have an instantaneous dipole. It exists just for an instant. But what happens? If this helium atom is next to this helium atom right here, once that little positive charge fills over here, it's going to make the electrons that are in this other helium atom pull toward the positive. They're going to pull over here. And when they pull toward the positive, now that creates another dipole. So this is called an induced dipole because this first guy turned this guy into a slight dipole because now the positive charge is here. We have the same situation that we did before. So now we have a little negative charge over here, partial negative, a partial positive that's over here, and that negative and that positive are going to attract together just for an instant because it's instantaneous. And so these instantaneous dipoles exist as the electrons sort of move around the atom, move around in a molecule if they're shared pair, and so they just happen to be more on one side than the other, which creates a temporary imbalance where there's more negative charge on one side, more positive on the other, creates a temporary dipole. Brief attractions between the instantaneous dipoles and the induced dipoles over here. And so then you can see how we have a positive attracts to a negative here. It's going to pull these 2 helium atoms together, which is the reason why helium can be a liquid if you cool it down enough. Because if you cool it down enough, you can slow these molecules down enough so that these little instantaneous dipoles, which create these London dispersion forces, will attract these together just enough to be able to get them to turn into a liquid form. And that's not just true for atoms. It also happens for molecules. Let's take H2. You know, this guy right here, hydrogen, it's 2 hydrogen atoms that are bonded together. They both have the same electronegativity, so it's going to be a neutral molecule. It's well, not neutral. It's going to be a non-polar molecule. And so as a result, you expect those electrons are going to be evenly spread out around the whole thing. But every so once in a while, what will end up happening is those electrons, though they're normally evenly spread out across the whole thing, will just happen to end up both on the same side. And so that shared pair will end up over here. It doesn't happen very often, but does happen here. And so when that happens is now we have a negative end and a positive end. We have a very, very brief dipole, that instantaneous dipole. And that positive end that's over here is going to pull the negatives on this one over to the side, making this side negative, and so we have a positive end and a negative end. And so that positive end is going to briefly attract over to that negative end right here, and it's going to pull these 2 hydrogen molecules together, these 2 H2 molecules together. And so that's how London dispersion forces work. Now, London dispersion forces are extremely weak. In terms of, if you had to talk about one single London dispersion force between 2 atoms, it's the weakest of all the types of intermolecular forces. But they are the most common, because they can exist between any atoms or any molecules. Okay? Unlike the dipole-dipole, in which you have to have 2 dipoles and they have to be aligned right so that a positive side is next to a negative side. You know, a dipole-dipole, if you put a positive next to a positive, they won't attract. But London dispersion is that this can happen anytime, with any molecule, any atom in there. So extremely, extremely common, even though they're extremely weak. Now, something that makes a big difference here is that if you have a large atom or a large molecule, those electrons are going to be spread out over a greater space because of the fact that the atom or the molecule is bigger. And so larger atoms tend to have stronger London forces than smaller atoms and molecules. Think of it a little like this. Let's compare our helium with, say, something that's a much, much larger atom. Let's say, I don't know, radon. Radon's a much bigger atom because of the fact that its valence electrons are way up in, let's see, 1, 2, 3, 4, 5, 6th energy level up there. And so that means that if radon's electrons end up all on one side, it's going to be a much bigger difference in distance across that than if helium's atoms end up right there. Those two are still pretty close to each other. And so we would end up with a much larger partial negative and a much larger partial positive charge on the radon than we would on the helium. And so the helium is going to be a much smaller dipole moment. It's going to have a much smaller dipole, much weaker polarity, and a much weaker dipole. And so that typically that's the rule. Larger atoms and larger molecules have stronger London forces. And so for very large molecules, the total of all the London forces are often greater than the dipole-dipole forces or even hydrogen bonding. So it's going to turn out that these, even though these London forces are extremely weak, they're actually the most important ones in terms of looking at intermolecular forces because they exist all the time, and especially for big molecules. For big molecules is that they're the dominant ones. For small molecules is that other things may matter. If you have a really tiny dipole or a really tiny hydrogen bonded thing, hydrogen bonding or the dipole forces are going to be the ones that are most important. Those are the strongest intermolecular forces. But for big molecules, because those electrons can spread out over the whole molecule, they can get way off balance, then you're going to end up with much stronger intermolecular forces for London forces. So let's rank these guys by the strength of the London dispersion forces. So helium, neon, argon, krypton, xenon. So we said the number one thing we look at is size. These are all atoms. So we want to look at the size of the atoms. So we look at helium. These are all the noble gases. Helium, neon, argon, krypton, xenon. And so what's our size here? Well, helium has electrons in the first energy level, valence electrons there. Neon has valence electrons in the second energy level, argon in the third energy level, krypton in the fourth energy level, xenon in the fifth energy level. So we would expect that the size is going to get larger because these electrons in the fifth energy level, their orbitals stick out farther. The helium, they don't stick out very far. And so we said that the larger the atom is, then the stronger the London dispersion forces, because with something like xenon, it's very easy for the electrons to get completely unbalanced, making a larger dipole, stronger dipole here. And so we would expect that since the size increases, helium, neon, argon, krypton, xenon, the strength of the London forces would also increase. And so then the London forces are also going to increase the strength. You can read that there. And so we expect a larger size, also larger London force strength. Let's try our next one. H2, N2, I2, Xe right here. So in this case we have molecules. So with molecules we don't want to just look at the overall, because we can't really sort of do our radius, our atomic radius, so we're not talking about atoms anymore. There's a good proxy for this, and that's to use atomic mass, or molecular mass. If you look at the molecular mass of these, we can compare them that way. So let's just go and figure out what are the molecular masses of these guys. So we don't have to be precise. We just need to get a general idea, and that'll give us a basic overall idea here. So H2, hydrogen is 1.01, so it's do 1. So two of those, 2 ones is 2 for the AMUs, for the atomic mass. Nitrogen is about 14. 14 times 2 is 28. Iodine, I2, iodine has an atomic mass of 126.9, so that's 127 times 2, which I think is what? 127 is 254 right there, so let's do 127 times 2, yep, 254. So iodine has a mass of 254. Xenon has a mass of 131.29. So we'll say 131. So comparing these guys here, the one that has the largest mass should be the one that has the strongest London forces. And so that's going to be iodine. So iodine is going to be number 1. Next largest is xenon. Xenon is going to be number 2. Next one is nitrogen. Nitrogen is number 3. Hydrogen then is going to be the weakest London dispersion forces. And so we'd expect that iodine would be the top one, xenon, nitrogen, hydrogen. And this actually makes sense because iodine of these 4 things here is the only one that's a liquid at room temperature. And the reason why is because it has a much larger mass, much larger London dispersion forces. It's able to pull those molecules together, and so it's more likely to stick together as a liquid instead of vaporizing into a gas like that. All right, next one up, CH4, C5H12, C10H22 are our next ones here. What's the ranking of their strength? Well, for London forces, we care once again about the size. They're all molecules, so we're going to look at the mass. So we don't actually have to calculate this because it's going to be pretty obvious which ones are the largest. That's got to be this one because it's got 10 carbons, 22 hydrogens. That's more carbons than anything else. It's more hydrogen than anything else. So that one's going to be the one that's the largest mass. So that one will have the strongest London dispersion forces. Then the next one is going to be this one. That one will have the second strongest London dispersion forces. And then CH4 will have to have the weakest because it has the smallest mass.